Right now, most people think they understand what's happening in the silver market. They look at the chart, they see volatility, they see prices moving up and then pulling back, and they assume the story is being written right there, on the screen, in real time, tick by tick. But that assumption is almost always wrong. Markets love price action. Traders react to candles. Headlines react to percentage moves. Commentators argue over support and resistance like it's the whole picture. But the most important forces shaping markets don't usually begin on price charts. They begin somewhere else entirely. Here's the disconnect. Price is what we see. Structure is what actually matters. Price moves fast. Structure moves slowly. And when those two fall out of sync, the chart becomes a distraction. History is full of moments like this. Moments where prices looked calm, or even weak, while something underneath the surface was quietly locking in. Factories were being built, contracts were being signed, supply chains were being re-engineered. By the time price finally reacted, the outcome was already decided. This is why markets so often feel sudden, not because change happens instantly, but because we weren't looking in the right place. When a structural shift begins, it doesn't announce itself with a spike. It doesn't ring a bell. It doesn't care whether traders are bullish or bearish. It starts with decisions that don't show up on a daily chart. Capital decisions, engineering decisions, material decisions, and that's where attention needs to move. Away from the screen, away from the noise, away from the assumption that price always tells the truth first. Because sometimes, price is late. Think about how most people interpret volatility. A sharp move down, they call it a rejection. A pullback, they call it a failed breakout. But volatility doesn't always mean weakness. Sometimes it simply means the market hasn't caught up yet. Structural problems don't begin with panic. They begin with alignment. When multiple long-term decisions quietly point in the same direction, when industries start planning years ahead based on the same assumptions, when systems commit to paths that are expensive or impossible to reverse, those commitments don't wait for market consensus. They happen regardless of sentiment, regardless of headlines, regardless of what the chart looks like today. And that's why focusing only on price can be misleading. Because price reflects what traders think right now. Structure reflects what the world is building for the next decade. Most people watch markets the way you watch weather. They react to today's conditions. But structural forces are more like climate. Slow to form, hard to change, and powerful once they're in motion. When climate shifts, the weather eventually follows. Always. Right now, silver prices are being watched, debated, argued over, but the more important question isn't what the price did this week. The real question is whether the foundations underneath that market are changing. Because if the foundation shifts, price doesn't get a vote. This is the mistake markets make over and over again. They assume today's signals explain tomorrow's reality. They assume the chart is the story, but charts are just reflections. They don't show intent. They don't show commitments. They don't show what's already been set in motion. And right now, something structural is quietly forming, far away from trading desks, far away from financial television, far away from the screens most people are staring at. It isn't loud, it isn't dramatic. But once it fully enters the market's field of view, it won't be subtle at all. Because by the time structural forces show up on price charts, they've already done their work. To understand what's actually happening, we need to separate two things that are often treated as the same: price and pressure. They are not identical. And most of the time, they don't even move together. When people talk about markets, they usually mean prices. What's something traded at today? What it closed at? How it moved compared to yesterday? That's the visible layer. But underneath that layer, there's another system operating on a completely different timeline. The physical system. Paper markets exist to express opinions. They reflect expectations, positioning, and sentiment. They are fast. They are liquid. They respond instantly to news, fear, and speculation. Physical supply chains are different. They move slowly. They respond to contracts, engineering constraints, and real-world availability. And once they commit, they don't reverse easily. This difference matters more than most people realize, because price can change in seconds. But physical systems take months, sometimes years, to adjust. History shows this gap over and over again. There are periods where price moves first, and the physical world scrambles to catch up. And there are periods where the physical world shifts quietly, while price lags behind, unaware of what's coming. Those second moments are the dangerous ones, not because something is being hidden, but because price simply hasn't been forced to respond yet. Think about how physical supply chains actually work. Raw materials are sourced under long-term agreements. Factories are designed around specific inputs. Production lines are optimized years in advance. These decisions are expensive. Once made, they lock in behavior. When a company commits to a material, it doesn't check the spot price every morning. It checks availability, reliability, consistency. Price volatility is noise. Supply certainty is everything. This is why physical buyers behave differently than traders. Traders can exit with a click. Manufacturers can't. If a factory depends on a specific input, that input must exist at any price. That's where pressure builds, not on screens. In procurement departments, in engineering meetings, in long-term planning documents that never make headlines. Paper markets react to information. Physical markets react to necessity. And necessity doesn't negotiate. This is why price is sometimes misleading. A stable price doesn't mean a stable system. A falling price doesn't mean demand disappeared. It often just means financial positioning shifted faster than physical reality. We've seen this before. In energy markets, in semiconductors, in critical materials that suddenly became non-optional. For long stretches, prices moved sideways, while the physical world was quietly tightening. Then, when the system finally reached its limit, price didn't adjust gradually. It jumped, not because something new happened, but because something old could no longer be ignored. This is the key idea. Pressure doesn't announce itself early. It accumulates. Paper markets can absorb stress for a long time. They do it by repricing risk, shifting contracts, and redistributing exposure. But physical systems don't have that flexibility. When material flow tightens, there are only three options: pay more, wait longer, or don't produce. And for industries that depend on continuous production, the third option doesn't exist. That's why the relationship between paper, price, and physical pressure is often delayed. Not distorted, delayed. Price is a signal, but it's a lagging one when it comes to structural change. This is where many market narratives go wrong. They assume that if price hasn't moved decisively, nothing important is happening. But that assumption only holds if price is the first place stress appears. Often, it isn't. The physical world tends to feel pressure first. Price responds later, sometimes violently. This gap is not a conspiracy. It's a timing issue. Financial markets trade expectations. Physical markets deal with consequences. When supply chains begin to tighten structurally, the early signs don't show up as spikes. They show up as longer lead times, as requests for guaranteed delivery, as buyers securing material earlier than they used to. These are not events traders see, but they are events manufacturers feel. And once those behaviors spread across an industry, the system changes, not overnight, but permanently. At that point, price doesn't drive behavior anymore. Behavior drives price. This is why analysts who focus exclusively on charts often miss inflection points. They are watching the reflection, not the source. Price tells you what traders think today. Physical commitments tell you what the world is building for tomorrow. When those two diverge, one of them has to adjust. And historically, it's price. Some pressures don't show up in price until there's nowhere left to hide. Because once physical systems reach their limit, there are no financial instruments that can fix it. No derivatives, no rollovers, no paper solutions. There is only material, or the lack of it. And when that moment arrives, the adjustment is rarely subtle. This is why understanding the difference between paper markets and physical supply chains matters so much right now. Because what looks like noise on a chart can be the calm before a structural shift becomes visible. In the next section, we're going to look at where that physical pressure actually starts. Not in markets, not in headlines, but in the decisions companies are making long before price reacts. If structural pressure doesn't start on price charts, then the next question becomes obvious. Where does it start? The answer is rarely found in headlines. It starts with decisions that don't need your attention, until it's too late to ignore them. One of the clearest signals comes from a place most people don't watch closely enough. Not consumer brands, not stock tickers. But the companies that sit deep inside the industrial stack, companies that don't sell stories, they sell components. Samsung SDI is one of those companies. It doesn't dominate headlines the way consumer electronics does, but it plays a central role in the global battery ecosystem. If you zoom out, Samsung SDI sits at a critical junction between materials, chemistry, and mass manufacturing. They don't just assemble batteries. They design systems that other industries depend on. Automakers, energy storage providers, electronics manufacturers. When Samsung SDI changes direction, downstream industries feel it, often years later. And that's why what's happening here matters. Not because of a press release, not because of a product demo, but because of where capital is being deployed. There's a rule in industrial economics that's worth remembering. Research explores possibilities. Factories lock in realities. Companies experiment with ideas all the time. Most of those ideas never leave the lab. But once a company starts committing capital to pilot lines, tooling, and specialized facilities, something changes. That's no longer exploration. That's commitment. Pilot lines are often misunderstood. People assume they're just scaled-up experiments. They're not. They're rehearsal. They exist to answer one question. Can this be produced reliably, repeatedly, and at scale? Building a pilot line means the company believes the chemistry works well enough to move forward. It means suppliers are being evaluated. Materials are being tested not just for performance, but for availability. And it means timelines are being set. This is where long-term signals live, not in marketing language, in infrastructure. Over the past few years, solid-state batteries have moved steadily from theory toward implementation, not in a single leap, but through a series of quiet steps: more funding, more partnerships, more testing, and eventually, physical space dedicated to production. That progression matters, because solid-state batteries have always promised a lot: higher energy density, improved safety, faster charging. But promises alone don't change industries. Execution does, and execution requires materials. This is where many people lose the plot. They think the story is about innovation, but innovation is only half the equation. The other half is constraint. When a company like Samsung SDI plans for next-generation battery production, it isn't just asking, can we make this work? It's asking, can we secure what this requires? Consistently. For years? That question forces a different kind of thinking. It forces procurement teams to look beyond current prices, beyond short-term volatility, toward long-term supply reliability, and that's where the quiet signal appears. Because long-term commitments don't respond to today's chart, they respond to tomorrow's bottlenecks. This is why factory construction matters so much. Factories are expensive. They are slow to build. And once they're built, they don't pivot easily. A facility designed around a specific chemistry can't simply swap materials without redesign, without requalification, without cost. So when companies move forward with production infrastructure, they're not placing a short-term bet. They're locking in assumptions about materials. This is the part most market participants miss. They focus on whether a technology is impressive, but they don't ask what that technology depends on. Every major industrial shift has a material footprint. Steel defined the Industrial Revolution. Oil defined the transportation era. Semiconductors define the digital age. Energy storage will be no different. Solid-state batteries aren't just an upgrade. They represent a different relationship between chemistry and scale. And that relationship has consequences. When companies start building factories, they're not betting on ideas. They're betting on materials. That bet doesn't show up on earnings calls. It shows up in supply agreements, in sourcing strategies, in the quiet reprioritization of inputs that most people never see. This is why signals from inside the industrial stack matter more than commentary from the outside. Engineers don't care about narratives. Procurement teams don't care about sentiment. They care about what works and whether they can get enough of it. Once those internal decisions align, the rest of the system eventually follows. Markets, prices, policy. But there's a delay, and that delay creates confusion. From the outside, everything looks normal. Prices move, markets argue, analysts debate. But from the inside, paths are being chosen. And once chosen, they're difficult to reverse. This is the quiet signal. Not loud enough to trend. Not dramatic enough to break news. but powerful enough to reshape supply chains. The reason it's easy to miss is because it doesn't demand attention. It doesn't ask to be believed. It simply proceeds. And when enough companies proceed in the same direction, the outcome stops being theoretical. It becomes structural. In the next section, we're going to look at why this particular technological shift places unusual pressure on specific materials, not because of hype, but because of how chemistry behaves at scale. Because once materials move from optional to essential, the entire equation changes. To understand why this moment is different, we need to slow down and talk about batteries. Not in the way engineers talk about them, in the way the system experiences them. For the last few decades, the world has run on lithium-ion batteries. They're everywhere. In your phone, in your laptop, in electric vehicles, in backup power systems. They've powered the modern world remarkably well, but they come with trade-offs. And those trade-offs are the reason this next transition matters. At a basic level, lithium-ion batteries rely on a liquid electrolyte. That liquid allows lithium ions to move back and forth during charging and discharging. It works, but it also creates limitations. Liquid electrolytes are flammable. They degrade over time, and they impose hard limits on how fast you can charge and how much energy you can safely store. This is why fast charging has always been a balancing act. Push it too hard, and something breaks. Not metaphorically, physically. One of the core problems has a name most people never hear: dendrites. Dendrites are tiny, needle-like structures that form inside batteries. They grow when lithium ions don't deposit evenly during charging. Instead of spreading smoothly, they concentrate. Over time, those needles can pierce internal barriers. When that happens, the battery shorts. Heat builds. Failure follows. This is why charging speed is limited. Why batteries degrade. Why safety systems exist in the first place. For years, engineers have known the solution in theory. Remove the liquid. Go solid state. Solid-state batteries replace the liquid electrolyte with a solid material. In theory, this eliminates flammability, improves stability, allows higher energy density, and enables much faster charging. On paper, it looks like the obvious next step. In practice, it's been incredibly difficult. For decades, solid-state batteries stayed trapped in laboratories. Not because companies weren't trying, but because the same problem kept coming back. Dendrites didn't disappear. They just changed form. Solid materials didn't magically solve uneven lithium deposition. In some cases, they made it worse. Researchers tried everything. Different solid electrolytes, different anode materials, different coatings and architectures. Each approach solved one problem and introduced another. This is why solid-state timelines kept slipping. Not because the idea was bad, but because the chemistry refused to cooperate. This is the part that matters for markets. Technology doesn't advance in a straight line. It advances in steps, when constraints are finally broken. And constraints in battery technology are physical. They are not policy choices. They are not pricing decisions. They are laws of chemistry. This is where materials stop being interchangeable. In many industries, substitution is easy. If one input becomes expensive, companies switch. Different alloy, different component, different supplier. Battery chemistry doesn't work that way. Not at this level. When a material is part of how ions move, part of how stability is maintained, part of how failure is prevented, you can't just swap it out. This is why solid-state batteries are different this time. Not because they're new, but because they push chemistry closer to its limits. As energy density increases, tolerances shrink. As charging speeds increase, margins disappear. As systems get smaller and more powerful, the room for compromise vanishes. At that point, materials stop being flexible. They become specific. This is where many market assumptions quietly break. People assume innovation will always find a workaround, that engineers will optimize away constraints, that cost pressure will force substitution. Sometimes that's true. Sometimes it isn't. When chemistry reaches a certain threshold, there are fewer degrees of freedom. Performance gains come at the cost of optionality. This is why solid-state batteries haven't been commercialized lightly. Every improvement has required precision. Every gain has tightened the system, and tighter systems are less forgiving. This is also why materials that once played minor roles can suddenly become critical, not because they're rare, But because their properties are difficult to replicate, at this stage, the question isn't whether solid-state batteries work, it's whether they can be produced reliably, at scale, without breaking something else. And that something else is often the supply chain. As batteries move from incremental improvement to structural redesign, they stop being modular. They become integrated systems. Chemistry, materials, and manufacturing are no longer separable. That integration is powerful, but it also creates pressure. Because once a design works, companies want to lock it in. They standardize it. They build around it. They scale it. And scaling removes flexibility. This is why solid-state batteries represent more than a technological upgrade. They represent a shift in how much freedom the system has. When everything works inside narrow tolerances, the cost of change rises. The cost of substitution rises. The cost of mistakes rises. This is where chemistry stops being flexible. At this point, markets don't get to vote, they adapt. The implications of this aren't visible yet, because we're still early in the transition. Pilot lines, limited deployments, gradual scaling, but the direction is set, and the constraints are real. In the next section, we're going to look at one material that sits directly inside this inflexible zone, not because it's fashionable, but because its properties matter in ways that can't easily be engineered away. That's where structural pressure begins to take shape. Up to this point, we've talked about systems, markets, factories, chemistry. Now we need to narrow the lens, because every complex system eventually comes down to a few critical variables. Sometimes, just one. In this case, that variable is silver, not as an investment, not as a symbol, but as a material. Silver has been part of industrial production for a very long time. Most people know it as a good conductor. That's true. But that description barely scratches the surface of why it matters. Silver isn't just conductive, it's consistently conductive, across temperature ranges, across stress conditions, across repeated cycles. That stability is rare. In most applications, silver plays a supporting role. Contacts, switches, connectors, small amounts, almost invisible. Because the quantities are small, the cost usually doesn't matter. Silver could double in price and most manufacturers wouldn't notice. They'd absorb it, or pass it on quietly. That's why silver has traditionally been treated as a background material. Important, but not decisive. But not all designs treat silver as a background player. Some designs place it directly inside the function of the system. This is the distinction that matters. Accessory versus functional. An accessory improves performance. A functional material enables performance. Remove an accessory, and the system still works, just worse. Remove a functional material, and the system fails. As technologies push closer to their physical limits, this distinction becomes critical. In high-stress environments, materials are chosen not because they're cheap, but because they're reliable. Silver's role in these environments comes from a combination of properties that are difficult to replicate simultaneously. High electrical conductivity, thermal stability, resistance to corrosion, predictable behavior under load. Other materials can match one or two of these traits. Very few can match all of them. That's why silver keeps reappearing in advanced designs. Not because engineers are nostalgic, but because physics keeps pointing them back to it. As systems become more compact, as energy density increases, as tolerances shrink, the margin for material substitution disappears. At that point, silver stops being a nice-to-have. It becomes a requirement. This is where many cost-based assumptions quietly break. People assume that if a material gets expensive, it will simply be engineered out. That assumption works, until it doesn't. There are moments in technology where optimization reaches a wall. Beyond that wall, performance gains demand specificity. Battery systems operating at higher energy densities are exactly that kind of environment. They don't tolerate variability well. They don't tolerate instability. They don't tolerate compromise. In those systems, materials aren't chosen for marketing reasons. They're chosen because alternatives fail testing. This is why silver's role is changing in certain designs. Not in name, in function. Instead of being sprinkled lightly across components, it moves closer to the core, closer to the processes that determine whether a system works at all. And that shift has consequences. When a material is peripheral, demand scales slowly. When a material is functional, demand scales with production. This is where scale matters more than quantity. Even small amounts per unit become meaningful when units multiply. Not because the material is suddenly scarce, but because demand behavior changes. Functional demand is less elastic. It doesn't respond quickly to price. It responds to necessity. Manufacturers don't ask, "Is silver expensive?" They ask, "Does this work without it?" If the answer is no, price becomes secondary. This is the part markets often underestimate. They treat silver like a commodity that behaves the way it always has. But commodities change behavior when their role changes. A material used decoratively behaves one way. A material used structurally behaves another. When silver is structural, the rules shift. This doesn't mean every design uses silver the same way. It doesn't mean every application consumes large amounts. It means the direction of use is changing, and direction matters more than magnitude at the beginning. Once a material becomes embedded in critical systems, it becomes difficult to remove. Standards form around it. Supply chains adapt to it. Manufacturing processes optimize for it. That's how lock-in happens. Not suddenly, gradually. This is why discussions about silver substitution often miss the point. They focus on theoretical alternatives, but theory doesn't run factories. Factories run on repeatability, on yield, on minimizing failure rates. If a material reduces failure risk, it earns its place. ADM, 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 even if it's not the cheapest option. This is the uncomfortable reality of advanced manufacturing. Cost matters until reliability matters more. In some systems, removing silver doesn't make them cheaper. It makes them fail. That's the line where silver stops behaving like a commodity and starts behaving like infrastructure. And infrastructure demand behaves differently. It doesn't spike on sentiment. It doesn't disappear when prices pull back. It persists as long as the system exists. At this stage, silver isn't the headline. It's the hinge. In the next section, we're going to step back and look at what happens when a functional material begins scaling across an entire industry. Not in theory, but in practice. Because once scale enters the picture, quiet pressures stop being quiet. Up to this point, everything we've talked about has been manageable. A material here, a design choice there, a single factory, a limited rollout. Nothing that sounds alarming on its own. And that's exactly why the next step matters. Because the real question isn't about one battery, it's about scale. Most technological transitions don't fail at the prototype stage. They fail or succeed at scale. When something moves from possible to mass-produced, at the unit level, everything looks small. A thin layer, a minor component, a fraction of the total system. Easy to dismiss. But industrial systems don't operate at the unit level. They operate at the factory level. And factories don't think in terms of grams or components. They think in terms of throughput. How many units per day? How many per year? How many over the lifetime of the facility? This is where perception breaks down. Because humans are good at understanding single objects, we're terrible at intuitively grasping multiplication at scale. One vehicle doesn't change anything. 10 vehicles don't either. Neither does 100. But 1,000,000? That's a different conversation. Now expand that thought. Not one factory, but dozens. Not one company, but an industry. This is how pressure forms without drama. Not through a spike, through accumulation. Every manufacturing system scales in layers. First, pilot production, then limited runs, then multiple facilities, then global replication. At each step, demand doesn't increase linearly. It steps up, and supply doesn't always follow at the same pace. This is where material systems begin to feel stress, not because each unit uses a lot, but because the total volume becomes meaningful. Small per unit, large at scale. That phrase shows up again and again in industrial analysis for a reason. It's the point where assumptions fail. People often ask the wrong question. They ask, is this material abundant? But abundance isn't the right metric. The right question is, can supply grow at the same rate as manufacturing? That's a very different problem. Battery manufacturing capacity has been expanding rapidly. New plants, new lines, new investments, all moving forward on timelines measured in years. Material supply systems move differently. They depend on geology, on extraction, on processing, on long lead times. These systems can expand, but not instantly, and not always in sync with downstream demand. This mismatch is subtle at first. You don't see it on charts. You feel it in lead times, in procurement strategies, in early commitments to future supply. This is why scaling questions matter so much. They force the system to reveal its limits. At low volumes, flexibility exists. At high volumes, choices harden. Manufacturers can tolerate experimentation early, but once scale begins, they need certainty. They need to know that the materials they depend on will be available, not just today, but years from now. This is where industries diverge. Some technologies scale cleanly, others run into bottlenecks, and bottlenecks don't announce themselves loudly. They show up as friction, as rising complexity, as competition for the same inputs. When multiple manufacturers scale the same technology at the same time, those frictions compound, not because anyone planned it, but because the system converged. This is why timing matters. If one company scaled alone, the system could adjust. But when an entire sector moves together, margins disappear. Supply systems that look comfortable suddenly feel tight, even without any dramatic change in availability. This is also why price is often late, because physical stress builds before financial stress. By the time price reflects what's happening, the underlying decisions are already locked in, factories built, processes standardized, production targets set. At that point, the system doesn't slow down easily. It pushes forward. This is where the scaling question becomes unavoidable, not as a headline, but as a reality. It's not about how much silver one battery needs. It's about what happens when millions are built. At that scale, even efficient designs generate meaningful demand, not because they're wasteful, but because multiplication changes everything. And this is where comparisons matter. Battery manufacturing capacity has been growing quickly. Material supply growth is steadier, more deliberate, more constrained. That difference doesn't create a crisis overnight. It creates pressure that accumulates quietly, until it reaches a point where adjustments become expensive. At that moment, markets react, sometimes smoothly, sometimes not, but by then, the math has already done its work. This is the part most people don't model correctly. They assume gradual adoption leads to gradual impact, but scaling doesn't behave that way. It moves in steps, and each step tightens the system. Once production reaches a certain threshold, the conversation changes. It stops being about if, it becomes about how. How do companies secure supply? How do they prioritize inputs? How do they protect production from disruption? Those questions don't wait for price confirmation. They arise from necessity, and necessity reshapes markets from the inside out. In the next section, we're going to look at how this kind of pressure differs from a traditional shortage, why it doesn't look dramatic at first, and why that makes it easy to underestimate. Because structural stress doesn't shout, it builds. At this point, it's important to slow the story down, not to weaken it, but to make it accurate, because what we're describing is not a collapse. It's not a doomsday scenario, and it's not the kind of crisis people imagine when they hear the word shortage. There's a critical distinction that often gets lost in market narratives: the difference between running out and falling out of sync. Most markets don't break because a material suddenly disappears. They strain because timing breaks. A true shortage is simple. There is nothing left. Production stops. Systems shut down. What we're talking about here is different. It's a bottleneck. A bottleneck doesn't mean there's no supply. It means supply can't move fast enough or flex easily enough to match what the system is asking for. And bottlenecks behave very differently from shortages. Shortages create panic. Bottlenecks create friction. Panic is loud. It shows up in headlines. It triggers emergency responses. Structural stress is quieter. It shows up in delays, in rising complexity, in companies competing for priority rather than volume. This is why framing matters. Because panic stories burn out quickly. Structural stories don't. Markets are actually very good at adapting to pressure. They substitute where they can. They optimize where possible. They delay where necessary, but they struggle when timing breaks. Timing breaks when multiple systems move at different speeds. Manufacturing scales faster than materials. Technology adoption accelerates faster than infrastructure. Demand shifts faster than supply chains were designed to handle. That's when stress accumulates, not all at once, but layer by layer. We've seen this pattern before, more than once. Take semiconductors. For years, chips were treated as interchangeable components, cheap, abundant, reliable. Then suddenly, they weren't. Not because silicon ran out, but because capacity couldn't expand fast enough. At the exact moment, demand surged across multiple industries. The result wasn't the end of electronics. It was delays, rationing, prioritization. Automakers waited. Consumer electronics competed. Prices adjusted. The system strained. It didn't collapse. Or consider palladium. For decades, it was a niche metal. Few people paid attention. Then emission standards tightened. Catalytic converters changed. Demand shifted structurally. Supply didn't vanish, but it couldn't respond quickly enough. The result wasn't panic. It was repricing. And eventually, substitution after years of adjustment. Rare earths tell a similar story. Not a material shortage. A timing and concentration problem. When supply chains realized how dependent they were on a narrow set of sources, the response wasn't immediate collapse. It was policy, diversification, long-term investment. In every case, the pattern is the same. Markets don't break when materials run out. They strain when timing breaks. That strain shows up first as inefficiency, then as competition, then as cost. This is why it's dangerous to frame everything as a crisis. Crisis language triggers short-term thinking. Structural pressure requires long-term analysis. And long-term analysis is exactly where most people stop paying attention. Structural stress doesn't feel urgent until it does. It doesn't force decisions overnight. It forces them gradually and expensively. Companies adapt, but adaptation has a cost. They redesign products. They renegotiate contracts. They secure supply earlier. They build buffers. All of that adds friction, and friction changes behavior. It changes how companies plan, how they price, how they allocate resources. This is where the real impact happens, not in headlines, in margins. And margins matter. A system under structural stress doesn't fail. It becomes less forgiving. Mistakes cost more. Delays ripple further. Suboptimal decisions compound. This is the environment we're describing, not one of collapse, but one of tightening constraints. And tightening constraints reshape markets, quietly, relentlessly. This is also why early stages are so easy to misread, because nothing looks broken yet. Production continues, products ship, prices move around, but underneath, the system is absorbing stress, and stress doesn't disappear on its own. It either gets relieved or it gets transferred. In the next section, we're going to look at who ultimately has to absorb that stress, not in theory, but in the real economy, because when systems strain, the pressure doesn't vanish, it moves. At this stage, the story stops being abstract. It stops being about materials, factories, or supply chains in isolation, and it starts becoming about consequences. Because when structural pressure builds, someone always has to absorb it. The system doesn't carry stress indefinitely. It passes it on. The first group that feels it isn't investors. It's manufacturers. Automakers operate on tight margins. Even the most successful ones. They manage costs carefully, years in advance. They lock in suppliers. They negotiate long-term agreements. They design vehicles around assumptions that stay fixed for an entire production cycle. When material dynamics change, automakers don't get to react instantly. They can't redesign a vehicle overnight. They can't retool a factory on short notice. They can't rewrite contracts already signed. So when pressure appears, their options are limited. They can try to absorb higher costs. They can delay rollouts. They can prioritize premium models where margins are thicker, or they can pass costs downstream. This is why material stress often shows up as price dispersion. Not everything gets more expensive at once. Some models disappear. Some trims become unavailable. Some technologies arrive slower than expected. From the outside, it looks like consumer choice. From the inside, it's triage. Long-term contracts become more valuable in this environment, not because they're cheaper, but because they provide certainty. Certainty becomes the scarce resource. This is also why automakers increasingly care about where materials come from. Not just how much they cost, but how reliable they are, how politically stable the supply is, how exposed it is to disruption. Which brings us to governments. Governments don't think in quarterly results. They think in timelines, election cycles, policy commitments, strategic goals. Energy transition targets are now embedded in law, not just in rhetoric. Mandates exist, incentives exist, deadlines exist. Those policies assume something critical, that the materials required for transition will be available when needed. When that assumption starts to wobble, governments face a dilemma. They can slow the transition, they can subsidize the difference, or they can intervene to secure supply. Historically, governments don't like to admit miscalculations. They prefer adjustment. That adjustment can take many forms: strategic stockpiles, domestic sourcing incentives, priority allocation for certain industries. Again, none of this looks dramatic at first. It looks administrative, technical, but it reshapes markets. When materials become strategically important, they stop behaving like ordinary commodities. They attract policy attention. They get classified differently. They become part of planning rather than trading. And then there are consumers. Consumers are usually the last to feel structural stress, but they do feel it. Not as shortages, as choices, fewer options, longer waits, higher prices for certain features, lower availability of others. From the consumer's perspective, nothing appears broken, but something feels tighter. This is how structural pressure enters everyday life, not as a crisis, as friction. You wait longer, you pay more, you compromise. And because these changes happen gradually, they're rarely connected back to materials. People blame companies. They blame inflation. They blame policy. Rarely do they trace the cause back to inputs. That's why this matters, not as a market call, but as a systems story. Structural pressure doesn't affect everyone equally. It moves through layers. Manufacturers first, governments next, consumers last. By the time consumers notice, the system has already adjusted, quietly. And that brings us to the final question. Throughout this story, we've avoided one thing intentionally: certainty. Because certainty is seductive. It feels confident, it feels decisive, and it's often wrong. What we're looking at isn't a single event. It's a convergence. Multiple industries, multiple timelines, multiple commitments, all leaning toward the same set of materials. No one planned it this way. It emerged naturally. Battery manufacturers pursued performance. Automakers pursued efficiency. Governments pursued transition. Each decision made sense on its own. But systems don't evaluate decisions in isolation. They aggregate them. This leads to the real question. Not whether one company made the right choice. Not whether one technology will dominate. But what happens when multiple industries bet on the same material? At the same time? History suggests the answer isn't catastrophe. It's constraint. Constraint forces prioritization. It forces trade-offs. It forces the system to reveal what it truly values. Some uses get protected, others get delayed. Prices adjust. Supply chains reconfigure. And eventually, new equilibrium forms. But that process isn't instant, and it isn't smooth. It happens through tension, through negotiation, through friction. This is why the most important signals don't come from price spikes. They come from behavior. Factories being built, contracts being extended, policies being rewritten. Those signals don't make headlines, but they matter more than headlines ever could. The biggest supply problems don't announce themselves. They don't arrive with sirens. They don't show up as breaking news. They arrive quietly, and then all at once. Not because the world ran out, but because timing finally caught up. This is the moment we're approaching, not a breaking point, a revealing point, where systems show their limits, where assumptions get tested, where flexibility narrows. What happens next isn't predetermined. Markets adapt, technology evolves, supply responds, but adaptation always has a cost, and understanding where that cost comes from and who ultimately pays it is the difference between watching the story unfold and actually understanding it.